Okay, before we get into a little bit of stuff on motion today, I want to talk really quickly about math and the math skills I expect you to have in this class, and do a couple examples on things that you may have forgotten or may not be 100% comfortable with. But I want to say really quickly a little bit about. Oh, look at that! Oh, that's the pen tool. I don't want that one. So I want to say really quickly a little about generally the math that you're going to need and not talk about some of these things. So for example, let's just make a list of the math skills that you need to have. In order to do physics, you need to like math, you need to enjoy math, because you can't really solve problems without math. You can understand physics pretty well if you skip the math. You know, you could get a good conceptual understanding, and we do that for some classes. Some of our courses are conceptual based. We don't really do equations. But to really, to be able to actually attach numbers to something, to quantify physical phenomena and things like that, of course you need math. So in this course, there's a few skills that you're going to need to be comfortable with. We talked about scientific notation, so I won't mention that yesterday. But you're going to need to be comfortable with geometry, right? I can't, there's another E in there. Spelling on this thing is funny. So you need to be comfortable with geometry. You need to be comfortable with algebra. You need to be comfortable with trig. And you need to be comfortable with vector math. I put vector math up here. You guys maybe haven't seen vector math, and we're going to spend a little bit of time talking about vector math, maybe tomorrow. But it's so important that you understand that there's a difference between vector math and math that I want you to get it in your head now, so that when you're dealing with vectors in the future, you're not trying to use basic scalar math that you're used to right now. Right? So these are the basic physics math concepts that you need to have a familiarity with. I would just want to kind of go into a little bit of detail on algebra and trig, and give you a couple refreshers on the trig, and then the same thing for algebra. And then geometry, it's circles and triangles and things like that. All right? Nothing up there. Everybody's taken a little bit of trig, geometry. Yeah, all right, good. All right, so it's a little bit of a refresher. So the part of algebra that I want to talk about, I don't want to spend a year dealing with college algebra. I want to focus specifically, obviously you should be able to solve algebraic equations, solving an equation for a variable or something like that. I want to focus though really quick on being able to solve simultaneous equations, simultaneously solve equations, or solve simultaneous equations. And what I mean by that is being able to solve two equations. That's an ugly S. For two unknowns. All right, so generally we won't work with more than two equations simultaneously. And what I mean by simultaneously is there's two unknowns that are consistent across both equations. You may have to solve a series of 2 or 3 or 5 equations, but each one will just have one variable that's missing. Right? In this case, I just want to talk about two equations for two unknowns. So I'm sure that you've all done this before, but I just want to give you a little refresher on how to go about this. So let's approach it from an example. So I've got an example written in my book here. So two equations, very general. 2a plus 2b is equal to 8. And then the other one was we're going to go with 1a plus 2b equals 5. This is totally day one stuff, but I was blabbing too much yesterday, so we didn't get to it. All right, so there's two ways you can approach solving a problem like this. All right, we want to solve for both a and b. We need two equations to do that. We have two equations, so we can solve this bad boy. The first way that you can solve this guy is basically add or subtract multiples of one equation from the other. All right, so what I mean by this is, let's do it here. I could just basically get rid of, what I want to do is I want to try to eliminate one of these terms. I have two variables in each equation that I don't know. I want to try to add or subtract one from the other so that I get rid of one of the variables. I have a third brand new equation, but it only has a single variable in it. So in this case, if you take a look at these equations, if I simply subtract, we'll call this equation number 1, we'll call this equation number 2. If I subtract equation 2 from equation 1, this 2b term is going to go away because there's a 2b in both equations. So if I do 1 minus 2, what that'll lead to is 2a minus 1a. Well, that's just 1a. And then I have 2b minus 2b, which is 0b, so that goes away. And then I have 3 over here on the right-hand side. A minus 5 is 3. So I'm left with a is equal to 3. All right? I think that this is the easiest way to solve simultaneous equations because you get a new equation that only has one variable that you don't know. It's not always obvious how to do that. In this case, it's very obvious because I have 2b in both equations. But sometimes you may not have a term that's the same and you might have to multiply by some factor. If I'm being really specific here, what I did is I multiplied 1 by equation 2. All right, so if multiplied by 1, nothing changes, but that's really what I did there is I took equation 2, multiplied it by 1, subtracted from equation 1. So now I have a solution for A. Of course, I need to go back in and plug this guy into one of my equations to get the solution for B. Doesn't matter which one you use, so I'll just pick equation 1. So now I can do 2 times 3 plus 2 times B is equal to 8. And if I just go ahead and solve like normal, I get 6 plus 2b is equal to 8. 2b is equal to 2. B is equal to 1. So my solution is A is equal to 3 and B is equal to 1. Right? I think that's the easier way to do simultaneous equations, but it isn't the only way. And sometimes you may be forced to use the second way just based on the complexity of the equation, or just it's not obvious how to do it. So the second way to do this then is to just solve one equation in terms of a variable. And there's nothing wrong with doing that. I can solve equation 1, which is up here, in terms of A or B, and then use that in equation 2. So let's go ahead and do that. That'd be really nice if I could. Is this going to work? All right, so there are my equations. So now I can go ahead and do the same thing. So I'll just solve equation again. This is 1, this is 1, this is 2. I'm going to solve equation, I'll solve equation 2 for A, or for A in terms of B, because that seems like the easy thing to do here. So all I'm doing is solving for A. Well, that's pretty easy. I just take 5 and I subtract 2B. Just rearrange the terms. And now I plug that back into equation 1 in A. So what I have then is 2 times A, which is actually 5 minus 2B, plus 2B equals 8. All right, and now just go through with my basic algebra skills. Multiply the 2 through 10 minus 4B plus 2B is equal to 8. I got 10, let's see, minus 2B equals 8. If I rearrange everything, I get 2B is equal to 2. B is equal to 1, which thank God I didn't screw up, because that looks like the answer we already got. And then once I have my equation for B, my solution for B, I plug it back into my equation for A. A is equal to 5 minus 2B, which is 5 minus 2, which is 3. So I got the same answer both ways. All right? Really quick review. You will have to do this. There's no doubt that you're going to have to do this in this course. It's going to be harder because you're going to also have to think about physics while doing this. So that's why I do it now really quick. All right? If this is stuff you're not comfortable with, make sure you review it after class tonight. Come see me, talk to Danielle, something. Talk to each other. But make sure that you're comfortable doing that. All right? Any questions on what I did? All right, cool. All right, let's do a really quick trig review. You're going to be loving trig in this course. We're going to use it all the time. We're just going to use trig in a very basic sense. Really, all that we're going to be doing is using trig for its awesome properties to relate sides and angles to triangles, to right triangles specifically. So you basically should, what you're going to be doing throughout the course is always, you will constantly be doing this. You will constantly break things into perpendicular components. And then you'll use the properties of right triangles. And then and that'll allow you to solve for different quantities that you're after, and you'll get to know these quantities. All right, so the key here is to be able to work with, right triangles. So let's draw a right triangle. Ooh, that's kind of a funny looking right triangle. All right, so we have a right triangle here. It's got a right angle down here. And I'm just going to work again with an example that I just making up here. We're going to let this be a 3, 4, 5 right triangle, because why not? Okay, now the first thing that you need to know is Pythagorean's theorem. Holy cow, P-Y. I'm a physicist, not a speller. Pythagorean. I'm getting lost already. That's not even close. Pythago. There should be a Pythag. That's closer. I should just scribble it. All right, Pythagorean theorem, which of course says if you have a right triangle with sides, we'll call this side A, this side B, and this side we'll call it C. That if you have the sides of a right triangle, you can figure out the hypotenuse using a squared plus b squared is equal to c squared. So if you're after the length of c, then you have to use the square root of a squared plus b squared. All right, so that should be ingrained in your brain somewhere. Pull it out, don't forget it, and you'll use that all the time. All right, in addition to that, you need to have some basic, you should know some basic trig identities. So let's that's an ugly line. I didn't mean to hit shift. Let's label that guy angle alpha. And if you know some of the sides, or if you know alpha, you could get the other sides or the angle. So depending on what you know, you could always find, as long as you know at least a side and an angle, then you can figure out the other sides. Or if you know two sides, then you can figure out all sides and all angles. All right, so in this case, we have an abundance of information, sort of like an abundance of Catherines. Anybody read John Green? It's an abundance of Catherines. Is that?
I haven't read that one.
I haven't read that one either, but it's on a list. John Green's a fantastic author. If you get a chance, read his books. His latest book is The Fault in Our Stars, which is really, really good. Yes. Oh, my book list, my personal book list that you care about deeply. All right, back to the task at hand. All right, so let's say that let's say that you want to find alpha. You know that alpha is related to the sides of this triangle by what? Sine of alpha. What's that equal to? Opposite over the hypotenuse. There we go. I knew it was in there somewhere. So opposite over the hypotenuse. In this case, that's equal to 3 divided by 5. That's good enough for this guy. All right, so that's equal to the opposite of the hypotenuse, cosine of alpha. Let's say you don't know the opposite, you only know the other angle. Well, the other angle would be the adjacent. So the cosine of the angle alpha is equal to the adjacent over the hypotenuse. In this case, the adjacent is side B, which is 4 over 5. Finally, the last option is the tangent of the angle alpha is equal to the opposite over the adjacent. My goodness. And that's just going to be 3 over 4. All right? Any three of these things will work. In this case, we know all the sides, so we could certainly use any of those to figure out the angle alpha. Once you know this, of course, this doesn't tell you much. How do I get the alpha? What operation do I have to use? Right, the inverse. So in this case, I need to apply the inverse sine, which looks like this on your calculator. In this case, I need to apply the inverse cosine. In this case, inverse tangent will get me the answer. And I guess just for completeness, we know the answer is 36.8 degrees, I believe. All right, fantastic time to mention that your calculator, it is super smart. It has both the ability to work in degrees and radians. So whenever you're working with angles, make sure that your calculator knows what you're working with, which unit you're working in. All right, it doesn't really matter which one as long as you get it right. And this is a great time to remind yourself that, hey, you could probably look at an angle in the book, a problem that you're working on, and sort of figure out whether or not the calculator is in the right units based on the answer that you get. If you're getting things like 0.0005 degrees, you might want to think about the fact that that could be in radians. You might be working in radians or something like that. All right. So this is generally all the trig that you're going to be using. Every now and again, I might mention like the law of cosines. I don't even know if I'm going to do that in this class at all. But there's other things that pop up from time to time. But this is the stuff that you're going to be using day in and day out, working with trig identities. So make sure you're very comfortable with working with these sorts of things. Again, it's easy. It might be easy for you now, but when we get into the physics, when we're using rotated coordinate systems and doing all sorts of crazy problems, it might all of a sudden become more complicated. So if it's easy now, that'll make it easier later. All right. And I did mention vectors, and so I just want to mention a little bit more about vectors before we get into things. We're going to come back and delve into this more later on, maybe tomorrow. But I want to point out the difference between two quantities that we're going to deal with in this course, scalars versus vectors. All right, so in physics, we deal with two types of quantities. We deal with scalars and vectors. It's important to recognize the difference because, again, it'll make life easier for you if you're comfortable with this now. All right? So a scalar is a number that you're used to, a number like you are used to dealing with. Specifically, it is a number that has a magnitude, and it is a number that has a unit. We don't deal with unitless numbers in here, so we're going to just say unit. All right? Vectors are a bit different because not only do they have a magnitude, they have what else?
A direction.
They have a direction. And they also have a unit. All right, and because of that direction thing, they require some special handling. They require some special math. All right, and we're going to talk a little bit more about that math a little bit later. We're going to come back to it. But I want to point out right now that anytime you see a vector, you can't use your normal means of adding and subtracting the numbers associated with that vector. All right, you have to handle them a little bit more carefully than that. And it's not terribly difficult, but it's just worth making sure that you're aware of now so that you don't have any issues with it. Okay. A couple examples of these types of numbers. So scalars, for example, mass. I got to stop pushing that button. Mass is one type of scalar that you'll use quite a bit. Who's got other examples of scalars? What's that? Meters is a unit, not a scalar. All right. So length is the associated unit for the meters. I'm not going to put length because that's kind of confusing because it can be a scalar or it can be a vector, really. What other quantities are scalars? Volume. That's a good one. So that's a little bit more specific than length. Time is a scalar. Though it does have a direction, it always moves in the same direction, I guess, as far as you're concerned. Anything else? There's a bunch of them. We can go on and on. I'll put density. I don't know. 4 seems like a good number to stop at. It's always arbitrary. All right, so those are a couple examples of scalars. What about vectors? What is examples of vectors? What do you think? What kind of a number has both a magnitude and a direction? Velocity. Good one. You'll note that whenever I write a vector, it's going to have a little vector arrow on top of it, like so. That's what velocity looks like. Man, it looks really nice in Illustrator. I like that. Other vectors? Acceleration. I'm going to be lazy. Write it like that. Force is indeed a vector. Right, good. So those are all vectors. I'll put momentum, another one that you'll see. Those are all examples of vectors, and there's many, many more that we'll come across. Right? As well as there are many more scalars.